In this video, we're going to look at what specific latent heat is and how to do calculations with latent heat. So when an object is having thermal energy provided to it, the temperature of that object increases until a certain point, and then there's a period of time where the temperature doesn't change. And this point here, represented by this flat line, this is representing a phase change. So this is when substance is either going from a solid to a liquid or a liquid to a gas. And what we find is while there's heat being provided to the substance, the temperature is not going up. And so we call that latent heat. The word latent means hidden. So the average kinetic energy of the molecules remains constant during this phase change. So that's why the temperature is not increasing. And so what's happening at this specific temperature is that all of the energy provided to the substance is going to increase the potential energy of the molecules. And that allows them to overcome their intermolecular forces, and that allows them to change phases. So that new energy could give a solid molecules more energy so that they're no longer solid and held together in a rigid place. They become a liquid and they can move more freely. Specific latent heat is the amount of energy required to change the state of 1 kilogram of a substance. It has a symbol L, and the unit is joules per kilogram. We have two different types. So when we're going from solid to liquid, we call that the latent heat of fusion. And when we're going from liquid to gas, we call that the latent heat of vaporization. The phase change equation gives us the thermal energy equal to the mass times the specific latent heat. And we're going to use this in the following questions to solve some problems. So in example 1, we have energy being provided to an ice cube of mass 20 grams, and we need to figure out how much energy that's going to take. So we are looking for thermal energy, so we're looking for Q in this case. We have 20 grams of ice, and so the mass is going to be 0.02, and the reason being is because the specific latent heat provided to us was in joules per kilogram, so we need those units to match up. So we do Q equals ml, and so that's 0.02 times 334,000, and that gives us a thermal energy of 6,680 joules, or writing it as one significant figure, we'd say the thermal energy provided is 7,000 joules. So in this question, we have 2.5 kilos of ice at -5 degrees Celsius, and we need to figure out the amount of energy to completely melt the ice block. And so this is going to happen in two steps. First, the ice will go from -5 up to 0 degrees Celsius, and then there will be that period where the ice is melting at 0 degrees Celsius. And so we need to figure out first the amount of energy in this part here, and then we need to add that to the amount of energy that's going to take here. And so for the first part to get from -5 to 0, that's going to be using the specific heat capacity because it's not a phase change. So the part where it's melting, the stage 1, we don't know how much energy that's going to take. The mass is 2.5 kilos. And the C in this case, the specific heat capacity for ice is 2108. And the change in temperature is going to be final minus initial. So it's 0 minus -5. So it's going to be 5 degrees Celsius. In the second part, Q2, when we're doing the phase change, we don't know how much energy that's going to take, but we know the mass is still 2.5 kilograms, and the specific latent heat of fusion is going to be 334,000. So the total energy to do all of this is going to be Q1 plus Q2, and Q1 is going to be 2.5 times 21808 times the change in temperature, which is 5, plus 2.5 times 334,000. And if we multiply and add those together, we get a total energy of 861,350 joules, or rounding to 2 sig figs, we're going to say 860,000 joules. Here we have a solid substance, has a mass of 1.2, and is being heated at a rate of 230 watts. We need to figure out the graph below to determine the latent heat of vaporization for this substance. And so we can tell by this graph, we know the latent heat of fusion is always at a lower temperature than vaporization. So what's going on here is this portion here, this is a solid, this is melting, so it's going from solid to liquid. This stage here, it's a liquid, And then this stage here, it's boiling. And the latent heat of vaporization occurs when it's boiling. So we need to figure out how much energy is being used to boil this 1.25 kilos, and then we can solve for L, the specific latent heat of fusion. So we're given 230 watts, and we know that power is the thermal energy provided over the time. So the total thermal energy is going to be power times time. So it's going to be 230 watts. And we know at this stage we're going from 950 seconds to 410 seconds. So that's the amount of time it takes. And so our total energy in this case is going to be 124,200 joules. And now we're looking for the specific latent heat of vaporization. So that's going to be rearranging that equation. We get L is equal to Q over M. So that's going to be 124,200 joules over 1.2 kilos. So that gives us a specific latent heat of vaporization of 103,500 joules per kilogram. And we'll do that to 2 sig figs. So we'll say 1.0 times 10 to the 5 joules per kilogram. So that's what our L is equal to. So in this question here, we have a block of ice at 0 degrees Celsius, and a 4-gram bullet also at 0 is fired into the ice, and it comes to rest. So the speed of the bullet just before is 415, and then we're going to estimate the amount of ice that's going to melt. And notice here they gave us specific latent heat of ice, but this time it's joules per grams, not joules per kilograms. And we got to pay attention to that later on when we're using these numbers. So a couple things. If the bullet and the ice are both at 0 degrees Celsius, that means when they come into contact, there's no thermal energy exchange because they're both already at the same temperature. So really what we're getting at with this question is that the kinetic energy of the bullet as it enters the ice is going to be converted into thermal energy, and then that thermal energy will melt the ice. And so we're trying to figure out how much kinetic energy the bullet has, and then how much ice would melt if that energy is the same. So for the bullet, we know the mass of the bullet is 4, and the speed of the bullet is 415. And we also know that L is 334 for this sample of ice, but we don't know the mass of ice. This is what we're looking for. What we can do is we can set that kinetic energy equal to the gain in thermal energy of the ice. So the kinetic energy is 1/2 mv squared, and that's going to equal ml. And the masses, I should make sure to distinguish, that's the mass of the bullet, and then this is the mass of the ice on the right side. So we have 1/2 times 4 times 415 squared, and that's going to equal the mass of ice times 334. And solving for the mass of ice, we get 1,031 grams. So rounding to 2 sig figures, we would say the mass of ice is going to be approximately 1.0 times 10 to the 3 grams. Okay, in this question we have 300 grams of ice at 0 and 450 grams of water at 21 degrees Celsius. And we have to determine the amount of ice left when it reaches equilibrium. And so the question gives us a bit of a clue, so we don't have to do any extra work. What it's indicating here from this question is that there's not enough thermal energy in the water to melt all of the ice. And so the equilibrium point is going to be 0 degrees Celsius. If there's ice remaining, that means it's remaining at 0 degrees Celsius. And so for water, we can determine the amount of energy lost by the water. Now the mass of water is 0.45 kilos, and the C is 4180, and the change in temperature for the water is 0 minus 21, so this is going to be negative 21 degrees Celsius. Now for the ice, we don't know how much ice is going to melt, and so the mass of the ice is one of our unknowns. The energy gained by the ice is going to be equated to the energy lost from the water, and then we have the specific latent heat of fusion for water, which is 334,000. So the energy gained by the ice is going to be equal to the energy lost by the water. And so now we have M times 334,000, and that's going to equal negative 0.454180 times negative 21, and that gives us a mass of 0.118 kilograms. And so this is the mass of ice that will melt. And the question asks us how much will be left. So then we figure out the mass left will be the 0.300, the 300 grams, minus the 0.118, and that leaves us with a mass of 0.182 grams. So that's how much ice will be left when it reaches equilibrium. Okay, so that was all about specific latent heat and how to use the phase change energy equation to do calculations related to phase changes and thermal energy changes.